Okay, now we're going to spend a little bit of time with integration. So if you'll write this theorem down, these are from your textbook as well. And these are the three ones that we're going to be using for a greater than 0. Like I said, this is covered in your textbook. I think it's theorem 8.9 in your textbook if you want to copy it from there. Okay, so after you get that down, we're just going to use this to be able to work some examples and take you through a few of those. Okay, so this is going to be our first example, evaluate the integral. So if you'll write that down, I'm going to pull the formulas up so we can look at them. Okay, so if we have these three to work with, which one do you think just, without doing a whole lot of work, would you think could possibly match this if we determined an a and a u? Definitely not this one, it doesn't have a square root, and this one also has a u on the outside. So my thought is that I'm going to be working with this, and I need to determine a u. Let's just see what happens if I say, let's let u be e to the x, because I know it's going to be a 1 here. So what would be u prime, or the derivative of u? Just e to the x dx, right? Okay, so if I was to rewrite this with the u, that would be 1 over 1 minus u squared, right? 1 minus u squared, but and also it might help you to see that this is actually a 1 is squared. 1 squared is just 1, but that's not necessarily intuitive when we write that. And then we have, since this is u, it would be du. So let's see if this representation, make sure that everything's accounted for here. So the du is e to the x dx, so that's the e to the x dx. That's fine. And then 1 minus the u squared would be e to the 2x. So this would be the case. So we're going to have sine inverse of u over a plus a constant. So that, when we evaluate that, it will give us sine inverse of u. What's u? What was our a? Yeah, good. A over here is the number that's squared. Well, in this case, it's 1. So does it matter? Do I need to put a u over a 1? No, u over a. So I'm just going to have sine inverse of u plus a constant. Also, we can remember if we used u representation, we can also, which our formulas are in u representation, so we don't necessarily have to go a step further, but if we wanted to, we could replace the u with the e to the x, but we don't necessarily have to. And our formulas are given in terms of u, so we'll just stop there. Okay, so the integral of 1 over x squared plus 16 dx. Let's pull our formulas. Okay, so which one of these does it look like could possibly match? The second one, right? There's no square roots, first of all, so I'm thinking it's going to be the tan inverse one. I have to determine what a is and what u is. Sometimes it helps to rewrite this. So if I rewrote this, what squared, so the a squared is first, which is the constant term, and the u is the variable in this case. So what if I just rearranged it? How could I rewrite 16? 4 squared. So, and I'm just going ahead and switching the order of those, plus x squared dx, or you could change it to the u there. What would our a and our u be in this case? So the a would be a 4, and the u would be that. So we can rewrite this as tan inverse. So it's going to be 1 over a, 1 over a. What was our a? 4, good, times the tan inverse, so we're using our formula now, tan inverse u, which is just x, and over a, again, which is 4, and then we have plus a constant. So we can make a note that u is equal to x and a is equal to 4 if that helps us when we plug into our formula. Okay, what if we extended number 2 a bit? This is the indefinite integral, and we got this solution. What if we extended it and I gave you a definite integral? We could then just take, let's pull this from the previous page, so if you'll help me carry this over, right? Okay, so let's just calculate this and see what kind of solution we get. I like to bring that 1/4 out front and then rewrite this as tan inverse. My first x is going to be a 4, and then I'm going to subtract tan inverse of, and my next one is going to be evaluated when x is 0, right? This simplifies to tan inverse of 1 minus tan inverse of 0. So if we use our skills from the last lesson and pull up this unit circle, what's the tan inverse of 1? Remember, tan region is over here. Sine over your cosine. Value is going to be 1, positive 1. So that would be this, right? Positive square root of 2 over 2 over that. It just simplifies to 1. So this is going to be pi fourths. So tan inverse of 1 is pi fourths. Now let's go find tan inverse of 0. Well, that's over here at 0. Okay, good. So let's just bring down that 1/4. And that's just going to give us 1/4 times pi fourths, which is just pi 16ths. So we can also be asked to calculate the definite integral with these as well. Okay, number 3. While you write that down, I'm going to go pull the formulas. Okay, first thing we want to do is we want to try to figure out if we can see which one's going to match. Like, so we'll have a goal in mind. What do you think it's looking like? Yeah, probably looking like this last one, but let's play with u and see if it helps. Let me let u equal to just x, because I'm thinking it's going here. So then what would u prime or du be? Just going to be 1 dx, or just 1. Okay, so if I were to rewrite that, well, that's real easy to see that that matches. That matches actually very nicely. So it's going to be 1 over a. What is a in our particular case? 1 squared is just 1, so your a is 1, so that would be like 1 over 1 secant inverse of what's u? It's just x. And what's a? We said was 1 plus a constant, so this just simplifies to secant inverse of x plus a constant. Okay, let's extend this a bit to a definite integral. So the same thing. Well, we can pull our previous work, so we can just say this is going to be secant inverse x. Evaluate it from here to here. Okay, so if I wrote that down, I can do that, or I can use my reciprocal and write it like this next step. All right, I actually prefer to work with it in terms of sines and cosines because this looks very familiar and it's right off my unit circle. So pull up your unit circle and tell me the cosine inverse of 1/2. So that is going to be pi thirds right there. So the x value is, so we're just going to say pi thirds. What about cosine inverse of the square root of 3 over 2? Pi 6. So we want to calculate pi thirds minus pi 6. If you get a common denominator there of a 6, then you're just going to simplify to pi 6. Okay, this is optional here. I just prefer that. Okay, our last example. I've done one of each so far, so if you will, actually I may have one more after this, but go ahead and try this one on your own. Good, it's going to be our sine inverse. So go ahead and be working with u and your du and see if you can get this solution. Okay, so labeling our u and u prom, rewriting it just so we can see our a more clearly, that our a is going to be 4. Then we'll have this, we'll pull it straight from our formula. And one more, last one, promise. Okay, I'll leave our formulas pulled up. So secant x, tan x, 1 plus secant squared x. Which one of these do you think it's similar to? Yeah, the second one. So see if you can figure out your a and your u and simplify this next one. Okay, so if we let our u be secant x, then u prom is secant x tangent x dx, which is nice because it's all of this. So if I rewrote that using a u, it would be 1 over 1 plus u squared. Very nicely matches this, where a is going to be 1 and x, so this is going to be tan inverse of just u plus c, because your a is 1. Alright, and that's a wrap.